Hello, my name is Ahmet Alacaoglu, and I'm going to present the last part of our tutorial, which is on adaptivity in min-max optimization. First, I'm going to talk about the problem that we want to solve in this case, which is a min-max problem where we have phi of xy as the coupling function, and x we will refer to as the primal variable, and y we will refer to as the dual variable. The main assumption about the problem that we will have is that this problem will be convex in x, the convex in min variable, and it will be concave in y, in the max variable. And the constraint set calligraphic x and y will be closed convex, and we will assume that the solution set is non-empty, which means that there exist primal and dual points x star, y star, such that the min-max value is achieved. If we look at this as a picture, we see that actually when we move along the x-axis while the y-axis is fixed, this surface will be convex. And when we do the same for y, meaning we will fix x and we will move along the y-axis, then the function, there will be a convex function. And the min-max value will essentially be here, which will be the saddle point. So we will call this point as the primal dual solution or the equilibrium point. So in this talk, we're going to explore the adaptivity ideas for solving such a problem. And to start off, we will first take a look at the classic methods. And on top of these methods, the adaptivity ideas will be built. And the simplest algorithm, similar to the use of gradient descent in the minimization case, here we will have gradient descent ascent. What this means is essentially in the min variable x, we will do a gradient descent step. And in the max variable y, we will do the gradient ascent step. And the way to do this, there are two ways. So the first one is the simultaneous way, which is also called forward-backward method. And in the simultaneous GDA, essentially what we do is that for both primal and dual updates, we use the same information. And the information is at iteration t, we will have our iterates xt and yt. And for both updates, xt plus 1 and yt plus 1, we use the same iterates. First, we will fix yt, and we will use xt and yt to do the update. Then we will do the same for yt, but they will happen at the same time. And the other way is to do this in an alternating way. And when we say alternating, we first do the primal update, xt plus 1 here. And when we are doing the dual update, we actually use the newest information. We will use the xt plus 1. In the simultaneous case, we used xt, and here we're using xt plus 1. So we hope that it will help us somehow. And so now we will see what do these algorithms do in a simple toy problem. And the problem in this case is that we will have one-dimensional dual and primal variables. So they're on the real line, x and y, and the coupling function is just multiplication of these variables. This is a bilinear problem. It's the simplest problem that we can think of. And unfortunately, both of the simultaneous and alternating GDA does not work in this case. Formally speaking, we have the results that with any constant step size, simultaneous GDA iterates will diverge geometrically. And on the other hand, when we do alternation, it will help. The iterates will not diverge, but they will not converge either. So essentially, the iterates will stay within a bounded distance from the solution, but they will not converge to the solution as shown in the following result. So with these results at hand, let's see what happens in practice. So when we go ahead and implement these methods on this simple problem, min max xy, and of course the solution in this case is the origin, and we look at the simultaneous case and we see that the iterates spiral outwards. Essentially, we see the divergence in the simultaneous case, and in the alternating case, as we see, the iterates stay in a certain distance from the optimum without converging to it. So we see a cycling behavior in the alternating GDA method. Now the question is, can we somehow fix these methods? And the answer turns out to be yes. And for this, we will do a little notational change. And essentially, we will stack the primal and dual variables. We will concatenate them to a single variable z, single vector z. And the calligraphic z, the constraint set for the z, will be the product of the primal and dual constraint set, calligraphic x and y. And the gradients that we used for our gradient descent, gradient ascent updates, the gradient of the coupling function with respect to x and y, we will also stack them together in the operator f. So this f operator applied to z, it will serve like a gradient in our case, and the minus sign for the gradient with respect to y is, it will allow us to write the update in a nice way. So with the notation at hand, we now go and write simultaneous GDA in essentially this almost the same way as the projected gradient descent. So f here serves as the gradient, which includes primal and dual gradients stacked together, concatenated together. And we do the gradient like update, then we do the projection. And of course, we can just plug in these definitions to see the same, to see that this update essentially does the same thing that we have written in the previous slide, which were showing the explicit updates for primal and dual. And now the simple modification that makes this method work is, like, one such modification is called extra gradient method. This is from 1976. And what the extra gradient method does is that on top of simultaneous GDA, it introduces an extrapolation step, which is the source of the name of extra gradient. So the main update is the second update. So we start from the current iter zt, and we go to the next iter zt plus 1, but the gradient, instead of taking gradient at zt as in the simultaneous case, we are now taking in the extrapolated iterate zt plus 1/2. And zt plus 1/2 is essentially the result when we do one simultaneous GDA step. And this seems abstract, so let's see what is happening in a simple example, and it's in the figure that we have here. So here we have the iterate zt, and we consider the simple bilinear problem again. And when we do the gradient step, if we just do the gradient step, this will take us to zt plus 1/2. And if we were doing the standard simultaneous GDA, then from zt plus 1/2, we would use the gradient here. We will move from this point to get the next one. But what we do in the extra gradient is that we first go to zt plus 1/2. Then we look at the gradient at that point. But then we go back to where we started zt, and we use the gradient at zt plus 1/2 to move from zt. And essentially what we see is that if we had taken the simultaneous GDA route, we would be getting away from the origin where the solution lies. But when we do the extra gradient, we are actually getting closer. So this is kind of an intuition why it might work, such a method. And essentially when we go and implement this method in this simple problem, and it seems to be converging to the origin, in this case, the iterate. So let us, now we have seen experimentally that this method should work in the bilinear case, but the question is, does it work in the convex concave setting that we wanted? And for this, I'm going to provide a unifying algorithm that I call stochastic extra gradient, just to be able to write both the standard deterministic method and possibly the method with noisy gradients, the stochastic method. So in this one, I will just write the same thing with variable step size, the only change, and I have f tilde here. And what f tilde is essentially, it's some form of approximation of f. It can be equal to f, which will give us the deterministic method, just no noise or no stochasticity, or we can have a noisy version of the f, which will be equal to the real f in expectation, and this would give us the stochastic problem, stochastic optimization kind of setting. Our assumptions will be similar to before. We will have convex concavity of the coupling function phi. We will have that a solution exists. So here we do not assume a unique solution exists. So it's like we have at least one solution. Solution set is non-empty. We will assume Lipschitzness of f. Recall that f was the gradient with respect to x and y, and essentially this assumption is telling us that our gradients in x and y in both variables, they will be Lipschitz. We will have unbiasedness, and also we will have variance bound, meaning that when we take our stochastic estimate of gradient and the real gradient, we take the norm squared, and in expectation it's bounded. These are rather standard requirements. Now the first result for stochastic extra gradient method in the deterministic case is due to Kerpelevich and Nemirovsky. So the first result states that when we have like perfect operators, so there's no noise, no stochasticity, we just use the full gradients as f is equal to f tilde. And in this case, we use as a constant step size, which will be smaller than 1 over L, where L was the Lipschitz constant of the gradients. And the first result is that we have convergence. So there exists a solution, Z star, such that our sequence converges to that. And the second result is on the rates. And essentially, we get that the averaged iterate converges at the rate of 1 over t. Here, the error function that I put here will be primal dual gap. I'm not going to get into the details of primal dual gap, but essentially it is the correct optimality measure for this problem, and it's enough for us to know this for the purposes of this part. So, and this rate is actually the optimal rate, 1 over t. And in the stochastic case, we have f tilde, which are the noisy oracles, noisy gradients, and they're in expectation equal to f. But normally they can be just noisy versions of f. But in this case, similar to stochastic gradient descent, we have to use a decreasing step size, essentially because of the variance. We have to push down the variance to 0. And the rate accordingly will be 1 over square root of t in this case. And the rate will be again on the expected primal dual gap. Now, on the average iterate, it will be 1 over square root of t. Now, let's move a bit further from the technicalities and look at the message of these results in terms of adaptivity, in terms of what we care about here. And essentially, what we have seen is that to get the optimal rates, 1 over t and 1 over square root of t in deterministic and stochastic cases, standard extra gradient needs to use 2 different step sizes. So it's a constant step size, 1 over L for deterministic, and it's a decreasing step size with square root of the iterate counter t in the stochastic setting. And another important point is that we need to know the Lipschitz constant L to be able to set the step size in the deterministic case. If you don't know L, you don't know how to set the step size to get the optimal rate. Now I will show how to get away, how to come up with an adaptive method that will not require this information and that will use one step size to get both of these results, both in the deterministic setting and in the stochastic setting, which means adaptivity to noise. And it will not require knowing the Lipschitz constant to set the step size. And this one, I repeat essentially extra gradient method, but I call it adaptive extra gradient because we are going to use an adaptive step size. And just as a reminder, I include the definition of f, which includes the gradients of the coupling function with respect to x and y. And the f tilde will be the stochastic noisy versions of these gradients. And the idea from Bach and Levy is that to set the step size eta t in the following way. So we have the domain diameter d in the numerator, and in the denominator we will have a constant g0 that we have to select, and we will accumulate for the iteration number t, we will accumulate all the occurrences of this capital Zi until t minus 1. And capital Zi will be a combination of iterate differences multiplied by the past step sizes. Now the definition of Zi especially can seem confusing or complicated. So let us try to build some intuition on how we come up with such a constant. And for that, we will do a little detour to Adagrad. So in Adagrad, for minimizing function f, our step size was domain diameter divided by square root, and we sum the observed gradient norm squares. And here the corresponding terms will be the sum of gradient norms and also sum of capital Zi's. So let's see how they are related in an intuitive level. So let's consider the unconstrained case where our constraint set is just the whole space. And essentially what we're going to show is that the Zi is of the same order as the norm of the f tilde, which is our gradient in this case. It's the quantity corresponding to the gradient. And to see this, we look at, for example, the iterative difference given here. And when we plug in the definitions of zi plus 1/2 and zi, and we take their difference, we get step size multiplied by the gradient evaluated at zi. So essentially, this is the reason for dividing by eta I, dividing by the step size in the definition of capital Zi, so that we will get something of the same order as the norm of the gradient operating f tilde. So this eta t is essentially a suitable step size, Adagrad-like step size that is that is for the minimax setting. So this is just, instead of the gradient, we have the iterative differences divided by the step size. And what Levy proved for this step size is that if we run this algorithm with a perfect oracle, meaning that our f tildes are just the full gradients, the deterministic oracle, and we use this adaptive step size given here, just using past information, past iterative differences, and essentially they show that they can get the optimal 1/t rate for the deterministic case. It's the same as the standard extra gradient. And in the stochastic case, when one feeds noisy inputs, f tilde, instead of the f, and again, we use the same step size, eta t, in equation 1, and the rate, the rate of the expected primal gap is 1/square of t. So what this means in our adaptivity analysis is that now we are using the same step size for deterministic and stochastic settings. We don't have to pick which step size to use. So we do not need to know if f tilde is noisy or not. We will just adapt to it by using the same step size. And essentially, we do not need to know the Lipschitz constant L. Our step size is independent of the Lipschitz constant. It only depends on the domain diameter and the observed information, observed iterates throughout the run of the algorithm. And just by using these algorithms, the algorithm will interpolate between the optimal rate in the stochastic setting, which is 1/square root of t, and optimal rate in the deterministic setting, which is 1/t. And what we have seen with the adaptive extra gradient was kind of a combination of extra gradient and Adagrad. And another similar idea has been to combine extra gradient with Adam. So what the difference of Adam from Adagrad was that we have one first order moment estimation of the observed gradients with the exponential moving average parameters beta 1, and also the second order, the element-wise square of the observed gradients with the parameter beta 2. And then we do a extra gradient step and the gradient step, main update step. So for this method, we do not have as a clear theoretical understanding as we had with the previous method, with the Adagrad plus extra gradient version. But we have seen actually compelling practical performance for training GANs. And one demonstration of this is for Alsan bedroom data sets. Like when we run extra Adam, what we get is that, again, similar to what we have checked in the first part, we can do simultaneous updates or we can do alternating updates here. And what we see is that simultaneous extra Adam actually does not give good practical performance, whereas alternated extra Adam performs quite well. It generates quite good looking images. Now we will move on to another notion of adaptivity, which will be adaptivity to strong convexity. So what we mean by that is that in the first part, we only assumed convex concavity. And under this assumption, the optimal rate was 1/t, and this is what we got. But in fact, when we have strong convexity, we can get linear convergence, similar to minimization setting. And now we will see how we can get this rate without the knowledge of strong convexity or without using strong convexity constants. So in this case, we will focus on a different problem template, which is of course similar to the first one. Here, instead of the general convex concave coupling function phi, we have a bilinear coupling term. And instead of the constraint sets in the first case, we have we have non-smooth convex functions. So we can see them as a regularized setting, whereas the first one was a constraint setting. These are essentially exchangeable in the algorithms that we are discussing here, but here having explicit functions will be more suitable for us in terms of the applications. So the assumptions are again similar. We have closed convex functions, and we have that solution set is non-empty. And examples of these problems, they come from minimization, both constraint minimization, like linear constraints, or TV regularized problems, or regularized empirical risk minimization problems, which we use Lagrange duality to pose as the bilinear min-max problem that we have here. And we rewrite the alternating GDA that we have seen in the beginning. And in this case, we are not writing it with projection, but we are writing it with prox operators because of the existence of non-smooth terms F and H. And essentially what we have is that we also use different step sizes, tau for primal step size and sigma for the dual step size. And we basically do a proximal gradient descent step in the primal variable. Then using the information, using the new iterate primal iterate, we are doing the proximal gradient ascent update. Now, a simple modification of this algorithm to make it work in this setting is due to Chambol and Pock in 2011, and it's called primal dual hybrid gradient. And the difference from alternating GDA is that instead of doing the primal step with the iterate YT, PDHG does the update in the linearly extrapolated iterate. 2YT, essentially, this is 2YT minus YT minus 1. So instead of YT, we also use the history and do a linear extrapolation and do the primal update using this. And what they showed is that with the constant steps, with constant step sizes tau and sigma, which use the norm of the gradient, norm of the matrix A, PDHG actually converges to the solution, and the rate will be 1 over t, similar to the previous to the extra gradient algorithm. And another, like when we look at the more structured setting of this bilinear problem, we can actually have a separable problem, meaning that the bilinear term is already separable, but if we also have the dual, the function in the dual, the h function, to be separable, then we can actually do more things. So, and essentially the problems that I have mentioned for this template, they are also satisfying the separable setting, essentially for linearly constrained problems, TV regularized problems, or most regularized empirical risk minimization problems that we use in practice. They are separable in the dual. So they will also fit into this problem, template. And in this case, what we can do is that we can do a randomized method. So we will essentially do something similar to coordinate descent based updates that we have in the minimization. We will see an appropriate application of these techniques for the primal dual setting. So essentially, this is this stochastic primal dual hybrid gradient algorithm is the randomized version of PDHG that we have seen in the previous slide. And what we do is that we first do the standard primal update, since we do not have a structure to exploit in the primal, but in the dual, we know that it's separable. So we can do randomized updates. So essentially, we pick one index from N, which is the dual dimension. Then for that index of the dual variable, we do the update, we do the proximal update. But for the other indices, we just keep the old iterate, YT. And to do this update in only one iterate, of course, we only need to access one function and also one row of a matrix here. We don't need to access the whole matrix. And then, of course, we have to do the extrapolation, the linear extrapolation. It's given in the specific form. We have YT plus 1, and we have the difference of YT plus 1 and YT. And we have to remember that YT and YT plus 1, they only differ in one coordinate because we do coordinate-based updates. And what we can show for this algorithm is that with constant step sizes, so this will be SPDHG with step sizes N is the dual dimension, and we have the multiplication of the primal step size and each dual step size. We are using different step sizes since we have separability in the dual, and the row norms of the AI they will be strictly smaller than 1. So this is kind of a similar step size rule as the deterministic one. And what we can show is that we have convergence of the iterate again to a solution. And in terms of rate, since we have randomization, we will have expected primal dual gap as the optimality measure, and this will go with the optimal 1/t rate. On the other hand, when the primal and dual functions are strongly convex, one can show faster linear convergence. But for this one, we have to use the step sizes tau and sigma r to be chosen depending on the strong convexity constants of F and strong convexity of constants of HI, which are given as mu I here. So the main message of this part is that for the SPDHG algorithm, we have to use different step sizes in the convex case and in the strongly convex case. So to interpolate between the sublinear 1/k rate and the linear rate, we have to change the step size. And the step size we need for the linear rate or for the strongly convex setting will depend on the strong convexity constant. So we have to know these constants to get the linear rate. And the question is, can we obtain this linear rate without using these constants or without using knowledge of strong convexity? And for that, we are going to use an assumption called metric subregularity, which is essentially kind of a generalization of strong convexity. So similar to error bound conditions that we have for minimization. And here, metric subregularity, the only thing we have to know about this assumption is that it's quite general. So one thing is satisfied for the strongly convex case. So it's satisfied, it covers the previously known results, which are applicable to strongly convex setting. But also this assumption holds when f and h are piecewise linear quadratic functions, and PL, which is abbreviated as PLQ, and PLQ has a quite broad number of examples, which include here indicator of polyhedral sets, polyhedral norms, such as L1 norm, hinge laws, Hubbard laws, which includes many of the loss functions that we use in practice. And what we can prove is that by using the same step size as our 1/t result, as our sublinear rate result, we can show that if metric subregularity holds and we use the same update rule, same step size selection rule, we again get linear convergence of the iterates. And here we have a little experiment to illustrate the linear convergence behavior and also the benefit of randomization. So we compare with the deterministic method, PDHG, and also stochastic method, SPDHG, for a basis pursuit problem with a synthetic setup. And what we see essentially is that we see a much faster convergence with the stochastic method in terms of epochs, and we also see actually linear convergence. And in the setting, we use this general step sizes. Since in the setting, metric subregularity will hold, we do not have strong convexity, strong concavity, and we do not know the constants, of course. So the main message of this part is that first, we know that randomization, we see now that in the structured settings, separable min-max setting, we can use randomization to speed up the algorithm PDHG without losing anything in theory, and in practice, we see much better performance. And the step sizes, we can use the same step sizes for the strongly convex case and for the standard convex case, and we do an interpolation between the linear rate and the sublinear rate with the same step sizes. And these step sizes do not depend on the strong convexity constants. Now we move on to the last notion of adaptivity that we will explore, and which will be this adaptivity to strong convexity, as we have just seen, and in addition, adaptivity to sparsity of the data, the potential sparsity of the data. So if we have further structure, in addition to separability, can we get faster algorithms? So to motivate this, I'm going to start with the SPDHG from stochastic primal block gradient method from the previous section for the, for the separable bilinear min-max problem. And we will now analyze the per iteration cost of this method. So in every iteration, what we do is that we compute the full primal update. And since the primal dimension is D, the cost will be D, because it's full vector update. And here we recall that we have the data matrix A, and from A1 to AN, we have its rows and each row has is in RD, of course. And the next step that we have to see the complexity of is the dual coordinate-wise dual updates. And in this one, we only have to access the selected row, and we just take an inner product with the primal iterate. So this will be the cost of the selected row. The cost will be the non-zeros of the selected row. And another thing we have to do is that we have to compute the extrapolated iterate. And essentially for this, we have to do we have to maintain this A transpose YT vector. And then by using this, since we have this vector, we just need to know how to do the update here. So essentially what we did here is that we added and subtracted YT here, and then we wrote it and we multiplied by A transpose and we wrote it in this way. So here what we know is that what we have to use is that YT plus 1 and YT, they only differ in the selected index IT. So we can use this information to only use that part of the matrix. We only use that row. And since we only use that one and we have essentially a sparse update here, we only, the update here will only depend on the number of non-zeros of the selected row. Because the other ones will be just zeros, and we will not need to do any updates on these ones. So the cost here will be dominated by the cost of computing the full primal iterate which will depend on the primal dimension. And the question here, can we do it? The only part that is costly here is this, and can we get around it? Can we make all the operations with the cost non-zeros of the selected row? To be able to obtain adaptivity to sparsity, we will have to use another algorithm, which is called pure CD. And what pure CD does is that, so similar to the PDHG, we have the primal and dual updates, which are essentially some little like GDA steps, gradient descent asset steps with little modifications. So here X bar and Y bar are the full iterates, but we actually do not need those. We just write them for like seeing the explicit updates, and they are not needed to run the algorithm. So essentially we pick an index for the dual, and we do update of the for the dual variable. We only do the update on that selected iterate. We take the corresponding value from the full updated iterate, and for the rest we just keep the old iterate. So from Y bar we only use Y bar at IT up to now. And for the primal update, recall that in the previous SPDHG we did the full update, and here we are going to do again coordinate-based update. And the way that we will decide which coordinate to update in the primal will depend on the sparsity. So essentially the capital J of IT is an index set. And it means that when we have selected an IT, which means we selected a row, and the capital J tells us in which indices of these of the row that we have non-zero elements. And essentially, we will only update the primal iterates that correspond to those indices. So in effect, this means that the number of coordinates of the primal vector that we are updating is the non-zeros of the selected row. And for the rest of the primal, we just keep them constant. Okay, when they are not in this index set. And the step sizes will be chosen. The step sizes, we will have coordinate-wise step sizes for both primal and dual here, tau I and sigma I, and they will be chosen using the non-zero entries of A. And essentially, when we do this, we will, in the dense setting, we will get the same step size as the SPDHG before. So this table is for SPDHG and this table is for pure CD. But iteration cost, for SPDHG, we had D before. But in this case, we are just going to have non-zeros of AI. So essentially, we can have significant improvement when D is large and A is sparse. And also, I'm not showing here for brevity, but the theoretical rates will be essentially almost the same as SPDHG. So we get as good theoretical guarantees as SPDHG. And let us see how this translates in practice. And for that, we are running lasso with different with data which has different levels of sparsity. So we have sparse, we have very sparse data for this. Density is 0.16%, and in the middle one, we have density of 4%, and in the rightmost one, we have density of 22%. So this is the most dense case. And as we see, when the data is dense, we see a similar performance between pure CD and SPDHG. SPDHG did not adapt to sparsity, but since when we have dense data, it doesn't matter much. But when we have sparse case, as we see, SPDHG gets much slower in terms of time, because per iteration, it will depend on D. Whereas pure CD will adapt to the sparsity. And since pure CD has the favorable performance in sparse and dense setting, it also does the optimal interpolation between these settings. And the other method that we compare here, which we denote as VCCD, is a method that adapts to sparsity, but it needs to use smaller step sizes than pure CD or SPDHG. So we see that in the dense setting, it's quite slow, but in the sparse setting, it can be better than SPDHG, but it's much worse than pure CD. This is what we observe. And the message of this part is that first, we see again that randomization speeds up the primal dual algorithm. And in addition to the previous part where we covered SPDHG, we have the unique benefit of pure CD, which is that both the per iteration cost and the step size, they depend on sparsity. So when we have sparse data, we both get better theoretical performance and also better practical performance. And in addition to that, similar to SPDHG, we use the same step size in the convex and strongly convex settings. Essentially, we use a step size which depends on the dual dimension and the row norms of the data matrix A. And we get the optimal sublinear rate, which is 1/t in the convex concave setting. And the same step size gives us linear convergence when we have further structure. And we do not need to know this further structural constants such as strong convexity. And we have a little summary slide here. Essentially, in this part, we have covered different notions of sparsity for min-max optimization. And we have seen that in the first approach, in the approach by Levy, which used Adagrad-like step sizes with extra gradients, we have seen that this method will adapt to Lipschitz constants of the gradients and also the noisy gradients. So we can interpolate between the 1/t rate of the deterministic case, convex concave case, and 1/√T rate of the stochastic case by using the same step size. But on the other hand, we do not know how this algorithm how this adaptive extra gradient behaves for strong convex case, or if it adapts to sparsity of the data or not. So, but on the other way, like when we focused on the bilinear problem, the separable problem, and we seen how we adapt to strong convexity to get linear rate, to interpolate between 1/t rate and the linear rate, or the sparsity of the data, we do not know how can we adapt to noisy gradients, or how can we adapt to the Lipschitz constants. For this methods, we still needed to use row norms, which are some forms of Lipschitz constants actually. So in this case, we know how to adapt to strong convexity and sparsity of the data, but we do not know the first two entries. So this is kind of an open question to come up with a method which can tick all the boxes. It does not exist now, and these are the current adaptive approaches that we have for min-max problems. So I'll be happy to take questions. Thank you for your time.